So greetings. So welcome to today's session. So if we recall, in the previous class, we were looking at the state space representation, right? So and then we stopped at the place where we had an equivalence between the transfer function and the state space realization, and the transfer function P of S was written as C dot Si minus A inverse P plus D, right? And we discussed that, like if we consider this inverse of Si minus A, that inverse is going to be the classical adjoint of Si minus A divided by determinant of Si minus A, right? So that's what is the expression for the inverse. And this P of S will anyway have the ratio of N of S and D of S, right? So we can immediately observe that under some conditions, like we are going to have the poles of the transfer function and eigenvalues of the state matrix being one and the same. Because if we solve determinant of Si minus A equals 0, we are essentially going to have eigenvalues of the state matrix A. Okay. So what is this definition of eigenvalue and eigenvector? I'm just recapping very briefly. So given, let's say, a matrix A, a non-trivial vector. Okay. So let me explain what this is. So a non-trivial vector V and a scalar lambda are called its eigenvector and eigenvalue respectively if the matrix A multiplying the vector B results in the scalar lambda multiplying the vector. Okay, so this is the definition of eigenvalue and eigenvector, right? So, and importantly, what we should note is that this V is a non-trivial vector. That means that V is not zero by definition. Okay, so the eigenvector is non-zero by definition. Okay, so that's something we need to remember. Okay, so this is the definition of an eigenvalue and an eigenvector. And if we essentially rearrange this term, so essentially we will get lambda I minus A times V is equal to 0. And essentially what this means is that if I call this as some matrix B, so this implies that the matrix B multiplying the vector V is equal to 0. And from linear algebra, when V is not 0, the only conclusion that we can draw is that the matrix B is singular. Okay, that is the conclusion that we can draw from linear algebra and matrix theory. So when matrix B is singular, its determinant becomes equal to 0. Okay, and that is the reason why we use determinant of lambda I minus A equals 0 to solve for the eigenvalues of the matrix, right? So okay, so I hope the reason behind this formula is clear. So that is the same formula we have written here, right? So instead of lambda, I have used S. Okay, so that's all. Okay, so I hope it's clear what is the definition of the eigenvalue of a matrix and its corresponding eigenvector. Okay, so before we go into the next module on mechanics, let me briefly do an example which sort of illustrates this equivalence between the state space and the transfer function representation. Okay, so let us consider the mass spring damper system. Okay, and let us essentially illustrate the equivalence between the state space and the transfer function representation. So let us consider the mass spring damper system. Okay, so for this system, recall that the plant transfer function P of S is 1 divided by ms square plus cs plus a. Okay, the state matrix A was 0, 1, minus k by m minus c by m. I'm just writing down things which we are already familiar with, right? And the input vector B is 0 and okay, and the output vector C is 1 and 0. And anyway, the direct transmission term is 0, okay, for this particular problem. Okay. So given this, let us verify this relationship. Okay, P of S is equal to C dot Si minus A inverse B times okay, so let's problem. All right. So first let us calculate Si minus A. So if I have to calculate Si minus A, what happens? So I will consider a 2 by 2 identity matrix. So Si minus A will just become this. Yes, minus 1 K by M and S plus C by M. Okay, so that's what will happen to S. Okay, so and its inverse is going to be what to say, adjoint divided by the determinant. So if I calculate the determinant of Si minus A, it's pretty simple, right? Why? Because it's just the cross product of the diagonal term and subtract the product, sorry, not cross product of the diagonal term and then subtract the product of the off diagonal terms, right? So this is a 2 by 2 matrix. So what will we get? We'll get S times S plus Cm minus 1 times K by M. Okay, so this is what we will have. So if we simplify this, we are going to get S squared plus C by MS plus K by M. Okay, so this can be written as MS squared plus CS plus K, the whole thing divided by M. I'm sure we understand how we got this, right? So we just simplify this, right? So now, how do I get the inverse? For the inverse, I need to first find the adjoint. So for a 2 by 2 matrix, what happens is that the adjoint is very simple. We just swap the diagonal terms and multiply the off diagonal terms by minus 1. Okay, so that is the result from matrix algebra. So essentially, we swap the off diagonal terms, S and S plus Cm. And off diagonal terms, we just multiply by minus 1. Okay, so this will give us the adjoint of S minus A for a 2 by 2 matrix. Okay, so let me be very careful here. Okay, so this is true only for a 2 by 2 matrix. So we get this, right? So then what happens to Si minus A inverse? It is 1 by determinant of Si minus A times adjoint, right? So what will I get? I will get M divided by ms squared plus cs plus k. This is 1 by determinant of S minus A. Multiply the adjoint of it will be C plus S plus C by M minus K by M. Yes. Okay. So now first let's do Si minus A inverse times B. Okay. So here we will do one step at a time. Okay. The first operation that we need to look at is Si minus A inverse B. So that will be M divided by ms squared plus cs plus k, first term. Then I have the matrix Si minus A, sorry, S plus C by M, 1 minus K by M and S. Okay, this will be the X matrix. And then like B will be 0 and 1 by M. Okay, and this will, if I simplify this matrix vector product, what am I going to get? First term will be the same, right? Then this will become a vector, right? So S plus 3 by M times 0 plus 1 times 1 by M. So the first element will become 1 by M. And the second row multiplying the column vector will result in minus K by M times 0, which is 0. And then S times 1 by M, I will get S by M. Okay, so this is what we will have. Okay, so this is what we have. Now we go and look at C dot Si minus A inverse B. Okay, so that is the next step. Of course, D here is 0, so that's why I'm not evaluating D. So anyway, m by ms squared plus cs plus k is a scalar valued function of s. So I can pull it out, no problem. The vector c is anyway 1 and 0, right? And si minus a inverse times b is, we just derived it as 1 by m and s by m. So we get this. So now what will happen if I now go and complete this derivation? I'm going to get m divided by ms square plus cs plus k, and then I will have 1 by m. Okay, because I will have 1 times 1 by m plus 0 times s by m, right? So the second term vanishes, I will only get 1. So now this m and this m cancel off. So what are we going to get? We are going to get 1 divided by ms square plus cs plus k, which we know is the Planck transfer. So we have just verified that equation, right, between the Planck transfer function and the state space realization through the simple example. Just an illustration of that equation, right? So P of s is going to be equal to C dot Si minus A inverse B plus D. In this particular case, D is essentially equal to 0, all right? I think so essentially we are evaluating only C dot Si minus A inverse B, all right? And that's going to be equal to the Planck transfer function. So we have checked the equation, okay, for this particular example. This is just an example illustration. Any questions on this before we go to the next module?
Sir,
Please
hello?
go ahead.
Yes,
Please go
sir.
ahead. Yeah.
In last class, when we started state representation, so you told us that we need to select two variables, state variables.
Yes, yes, yes.
And you selected position and velocity as a state parameter, right?
Yes.
So why can't we choose velocity and acceleration as a parameter?
So if you choose velocity and acceleration, let's say, for this, what to say now, let me learn from last time, and I will use Z as the displacement for the mass spring damper system. Okay, so let us say, let's consider this, right? Is it not? This is the equation of motion for the 1 degree of freedom mass spring damper system with Z being the displacement. So now, according to your question, let's say we consider these two as the state variables. Am I correct? The speed and the acceleration, right?
Yes.
Now, the state space process requires that we take the first derivative of both state variables. So x1 dot will become z dot double dot. That will become equal to x2. No problem, right?
Mm-hmm.
However, if you come to x2 dot, what is going to happen?
Z triple dot.
Get x triple dot. How do we get an equation for this? Right? Yeah. Correct. So we are unable to write an equation for this. Of course, one can always say, hey, differentiate the ODE and then write it. But then, like, we get into further problems, right? Is it not? Right? We will then need f dot. Correct? Yeah.
Yes, sir.
Right. So that's why we choose speed and displacement, or displacement and speed as the two state. Is it fine?
Yes, sir. So, sir, can we generalize that that we always choose a state parameter as one derivative less than the equation?
I'm sorry, what is it?
So can we generalize it by saying that when we choose the state parameters, so the highest derivative of the state parameters should be one less than the order of the equation?
So yeah, if you have motion systems, right? Yeah, like this, right? So then you say that what you are saying is makes sense. That is, like, you are essentially saying that the state variables should be chosen such that the highest derivative which appears in the state variable be one less than the order of the highest derivative that appears in the governing equation. Right?
Yes,
so
sir.
that's what it is. Correct. That's okay. And anyway, when we go to automotive controls, you would see that this state space representation that is non-unique. So what do I mean by that? So let us say there are 7 of us in this meeting, right? So for the mass spring damper system, each one of us will get the same answer, okay, the same transfer function, okay, as far as deriving the transfer function. But each one of us can write our own state space. Okay, so we will see why, how, and all when we go to control of automatic systems. Okay, so the state space representation is not unique, but the transfer function representation is unique. Okay, so that is also another characteristics that we need to cover. And we will see that we will also exploit the non-uniqueness of the state space representation to our advantage, okay, by doing some transformations and also like that will ease the computations we do when we implement things in real life. Okay, yeah. But those are concepts we will learn in the next course on control of automatic systems. Right?
Okay, sir. Thank you.
Okay. Any other questions?
Sir, actually, this is regarding assignment 2, like a B. So when we
Yes,
have
please.
an input is like a differentiation, then
Ah,
actually there we couldn't solve this question, sir. I couldn't
very
solve
good.
this question.
Very good, very good. So I think I was waiting for that question to come. That's why I have
Okay.
also like kept the homework submission open, right? I have not closed it yet, right? So
Yeah.
please think about it, right? So
Yeah.
see, I also want to what to say, want you to think through, right? And figure out, like how you can, right? Because see, in that problem, we had that u dot term, right? Yeah.
Yes, sir.
So I will give you a hint. You need to ensure that you redefine x2 as not just y dot, okay, but some function involving y dot and u, so that when you take the derivative of x2, you will get y double dot and u dot, okay, and that you can use to simplify this. Okay?
Sure, sir. Yeah, I'll try that.
Let me give you that hint. Okay,
Yeah.
so you're right. Like if you just chose x1 to be y and x2 to be y dot, we will have a u dot term in the x2 dot equation, right? That's where I'm sure you will be stuck. Right? Is it wrong?
Yeah.
Correct. So that is why I'm saying. So the first choice would have been for everyone to choose x1 to be y, x2 to be equal to y dot. Okay, but unfortunately, this would not have worked. Okay, so what I am suggesting is that like choose x2 to be a function involving y dot and u, such that things become easier. Right?
Sure, sir. Yeah. Thank you.
Okay, so please try.
Yeah.
So
So
as I
when
mentioned, please go ahead.
so when we choose the state variables, it was always the position and the velocity, right? So how we can
Ah,
incorporate output of in that state variables?
so may not be position and speed, like we just chose based on some physical intuition. All right. Y can be a what to say non-physical variable also. Okay. And you can choose state variables which need not have any physical connotation. Okay. That's one more feature of state variable. So yeah. Okay, so I'm not going through all those details in this course. As I mentioned, we will study a few more aspects in the auto control course. However, the state variable definition can also include the input. What you cannot have is that, like in the state equation, the derivative of the input coming into play, right? So, okay, nice questions. Any further questions? Okay, so now let's move to our second module. Okay, so this module is going to be on mechanics. So we have been looking at dynamic systems till now. The reason why we have been looking at dynamic systems is that, like anyway, even in vehicle dynamics, we look at vehicles as an entity or object to which we provide some input and we expect some output from it, right? So that's what this essentially our visualization or motion is concerned, right? But then if we look at the concepts that we learned in dynamic systems, like they will help us in sort of like visualizing even vehicle dynamics from that perspective. So that is why we learned some key concepts associated with dynamic systems. Okay, that is now, like having looked at the notion of dynamic systems, right, or the main concepts behind dynamic systems. Let's go to the second module, and then let's look at some core concepts related to mechanics. Once again, it's going to be a recap of things, but I'm going to recap important concepts, that we will be. Okay, so that's what it. So now, first, let's look at mechanics. It's by itself, and there are some key branches of mechanics, right? So what are the key branches of mechanics? First one is statics. Okay, the statics essentially deals with analysis of forces or moments or torques, right, on bodies that are in a state of equilibrium. Okay, so that's what we do in statics, right? See, for example, we would have analyzed, if you recall our undergraduate courses in mechanics, we would have analyzed bridges, where assume it to be almost static, and then we essentially do the force and moment balance, right? So when they are in equilibrium condition. Okay, so that's what we learn in statics. That's one key component of mechanics. Then we go to kinematics. So what do we essentially do in kinematics? We essentially study the motion of objects without considering what causes the motion. Okay, so suppose, let us say, even if I have a vehicle, right? So, and I steer the vehicle. When we are going to look at steering kinematics, we are not going to figure out how the vehicle heading is changed by applying some force and moments on, right? Rather, we are only going to consider the displacement, speeds, and accelerations of, right? So that's what we are going to do in kinematics. So kinematics deals with the study of motion of bodies without considering cause for the same. Okay, so that's what they provide, right? As far as that's what we do in kinematics. Okay, then comes what is called kinetics. Okay, what is kinetics? Kinetics, we essentially consider the forces slash moments, right, or torques that act on the body and the motion that they cause, right, and the resulting motion. So we consider the forces, torques acting on bodies and the resulting motion. Okay, so that is what we consider in kinetics. And so these are broadly the three broad areas of mechanics. Of course, with time, different people group things differently. As far as we are concerned, we are essentially going to group kinematics and kinetics into dynamics, and that's what we are going to study. And that's why people will call it as statics and dynamics of mechanical systems and so on, right? So statics is when there is when the objects are in equilibrium state, and then when there is motion and when there is essentially deviation from the equilibrium state, we are going to look at kinematics and kinetics. Okay, so those are the broad categories of mechanics. Okay, and as far as our course on vehicle dynamics is concerned, we will be dealing with what is called as classical Newtonian mechanics. So what is this classical Newtonian mechanics? Okay, so as the name indicates, this is a field of mechanics where Newton has made significant contribution before Newton Galileo, right? So let's see what this classical Newtonian mechanics is concerned with. So in classical Newtonian mechanics, we deal with macroscopic systems. That is like we don't go into the atomic or subatomic level. So we are going to deal with macroscopic systems. That is as far as size is concerned. And then we are going to consider non-relativistic effects, okay, or non-relativistic phenomena. So what do we mean by non-relativistic motion? So that means that velocities are very small in magnitude. Of course, I'm using many words and quotes so that like we take it in the correct spirit. Okay, very small in magnitude and compared with the speed of light. Okay, so that's what we are going to call as a non-relativistic phenomenon or non-relativistic motion. Okay, so and that's what happens in anyway vehicles, right? So we are going to deal with the lump bodies, right? So which are certainly not subatomic, and we are essentially going to work at speeds which are much lower than the speed of light. If you recall, the speed of light under standard conditions is going to be on the order of 3 into 10 power 8 meters per second. Okay, so certainly our vehicles are not going to go at road vehicles are not going to go at that speed. So we are okay, right? Okay. So now, having looked at briefly recalled what is classical mechanics, okay? So Newtonian mechanics. So let's also recap some more terms. Okay? So that's what is going to be the main object of today's class. So we'll also define what is called as an inertial frame of reference. I'm sure all of us would have heard about these terms somewhere or the other. So what is an inertial frame of reference? Okay. So what is a frame of reference? Okay. So a frame of reference is one with respect to which we measure variables. We fix a coordinate system and then like we measure variables that characterize the motion of it, right? So so what is this inertial frame? Okay. So an inertial frame is a frame that is addressed or moving uniform velocity okay, relative to an average position of distant fixed stars. Okay, so these are all like a very vaguely defined terms, but then like it is okay for our application, right? So, sorry, fixed stars. Okay, so sometimes, like more than vaguely, they may be sort of like axiomatic definitions, right? So what do we mean by axiomatic definitions? We take them to be correct, like so we don't explicitly question them, like we take them to be correct and then like we go ahead, right? So that's what we are going to do. So that is what is called as an inertial frame of reference, right? And of course, but then like in anyway in vehicles, like we are going to take measurements with respect to frames of references, like that are essentially connected to the Earth's surface, right, or present on the Earth's surface, right? And we consider them to be almost inertial because if you look at for the applications under consideration, although the Earth rotates about its axis and then it also rotates about the sun, revolves around the sun, right? So the accelerations are not significant enough for our application to be factored in. Okay, so when we consider the what to say motion of road vehicles. Okay, so that is why we typically make that approximations. Okay, but however, like for the sake of convenience, we have several body fixed frame of references. Okay, so what is a body fixed frame of reference? Many times, like we measure quantities by attaching coordinate frames, right, or frames of reference to specific points in the body under steering. Okay. See, for example, for us, we are dealing with road vehicles, like we may attach body fixed frame of reference to the vehicle's center of mass. Okay, so that is one option. Okay, and we may measure quantities by attaching body fixed frame of reference to the wheels. Okay, we may attach coordinate systems or coordinate frames to the tire rod interface center contact point. Okay, sometimes it makes sense for us to do that, right? So we may have all these different frames of references, right? And then measure quantities. Of course, can we use them? Obviously, you know, like we can measure quantities with respect to any frame of reference. But however, why do we typically measure things with respect to an inertial frame of reference? It is just that the governing equations of motion, okay, for that characterizes a body's or a vehicle's motion in our case, take the simplest form when we write those equations with respect to an inertial frame. Okay, so that is the bottom line. Okay, so we can use any other frame of reference and then like write down equations of motion with respect to quantities measured with respect to that frame of reference, but we may have additional terms coming into these equations, right? So, but then if we write equations of motion with respect to an inertial frame of reference, it so turns out that the governing equations take the simplest form when written with respect to an inertial frame of reference. Okay, so that is why we typically choose an inertial frame of reference and write down all the governing equations of. Okay, so that is one. So now we have introduced another some other terms, right? Center of mass and center of gravity and so on, right? All those terms are also some things, you know, which we typically hear. So now, what is this center of mass? Like, let's abbreviate it as CM. Okay. So let me define the center of mass. It is the weighted average position of a system of particles or the continuum of particles that constitute a rigid surface. Continuum of particles that constitute a rigid surface. Okay, so in fact, center of mass is the weighted average position of a system of particles or a continuum of particles that constitute a rigid body. Okay, so if you want to visualize it, it is a notional point. Okay, so see, suppose let us say we are given a vehicle, right? You consider a car, right? What is the center of mass, right? It is a point, it's a notional point at which one could take the entire mass of the body to be concentrated so that we have a point mass and visualize the body's motion. Okay, although we know that a point doesn't have a dimension, right? But the car has fixed dimensions, right? So, but then we want to concentrate all the matter in the car at a single point, and that is the center of mass, right? So, it's a notional point. Sorry, no questions. Sorry about that. You know, it's a notional point at which the entire mass of the body is taken to be concentrated to visualize its movement. Okay, that's the center of mass. So if one were to essentially draw a very simple schematic, right? So to visualize the center of mass, so let me draw first a three-dimensional axis, okay, and then like let's essentially visualize this. Okay, so suppose let us say this is our x-axis, this is our y-axis, this is our z-axis. Okay, so and this is the origin. Now let us say that like I draw some arbitrary body. Okay, so this is my body in space. Okay, so let's say we use the script B to represent our body and state. Okay, it's a rigid body. Now let's say like this body has mass capital M. Okay, that's the total mass of the body. Now, let's consider an infinitesimally small point in the body. Okay, so whose mass is some dm. Okay, and let the position vector of this point from the origin be indicated by the position vector r. Okay, and let us say this point be the center of mass, and the position vector of the center of mass from the origin, let's say we call it as r, the vector r subscript cm. So let me repeat once again. So I consider an arbitrary body in space, in three-dimensional space, whose total mass is capital M. And then like what we do is that like we take an infinitesimal mass dm in this rigid body, and let's say the position vector of that infinitesimal mass being r, and let's say cm indicate the location of the center of mass of the body, and let rcm indicate the position vector of the center of mass of the body. Okay, so these are the two entities that we are going to be interested. Now the question becomes, given this, how can we get the position vector, the center of mass, right? So the position vector of the center of mass, okay, is given by follow. Okay, r subscript cm is going to be equal to 1 by capital M. Okay, and we integrate over the entire body the product of the vector position vector r with dm. Okay, so that's what we do. So what we do is that like we take the product of this position vector r, then multiplied by the infinitesimal mass dm, integrated over the entire body, and then we divide it by the total mass m. Okay, so that will give us the position of the position vector. Sorry, this position vector of the center of mass. Okay, so that's what it is. Okay. So this is the center of mass. So in essence, what we are dealing with is that like can I get the position of a single point, notional point, where the entire mass of the object is concentrated? Okay. Then what is the center of gravity? So I'm sure all of us would have heard this term multiple times, right? Whenever we deal with vehicles and vehicle dynamics, the CG location, right? So it is important for us to note the difference between center of mass and center of gravity, and then like also know when they are one and the same. Okay, so what is the center of gravity? Let me write on the definition. Okay, then I will tell you when they are the same. When the center of gravity and center of mass are the same. It is the point in a body where the resultant torque, gravity, vanishes. So this is what is called center of gravity. So many people mix center of mass and center of gravity, but in fact they are two different concepts. Please note that. Okay, the definitions are different, right? Center of mass is the position of a notional point, or indicates the position of a notional point where the entire body mass can be concentrated to visualize its motion, right? Whereas the center of gravity is that point in the body where the resultant torque due to gravity vanishes. Okay, it so turns out that when we have uniform gravitational field, as we are going to have in our application, like I'm considering the distribution of gravitational field on Earth and also the size of vehicles under study. So in the presence of an uniform gravitational field, okay, the CG coincides with the center of mass. Okay, so okay, so I think this difference is very key, right? So we can see that the center of gravity is a point in a body where the resultant torque due to gravity vanishes. So that is certainly different from center of mass. Okay, and but for our application, both coincide. Okay, so that is why now you can understand why we use it interchangeably. Okay, like when we essentially use center of mass, center of gravity interchangeably in our application. But please note that in general they are different. Okay, so we need to be aware of this. Okay, so now we go to Newton's second law of motion. Yeah. Any questions before we go ahead? All right. Okay. So I am going to write down the statement of Newton's law of motion, and all of us are familiar with the popular mathematical statement of Newton's second law of motion, right? F equals ma. Right? I'm going to write down the English statement. I'm going to pose a question to you and then let you think about it before we continue from there in the next class. But to begin with, let me write down the statement of Newton's second law of motion. So this Newton's second law of motion states that the time rate of change of linear momentum is directly proportional to the net force acting on a particle and is along same direction as this force. Okay, so that's the statement of Newton's second law of motion. Okay, so Newton's second law of motion states that the time rate of change of linear momentum is directly proportional to the net force acting on a particle and is along the same direction as this force. So, in fact, the linear momentum, which is once again a vector quantity. By the way, I hope all of us remember our notation, right? So when we put a tilde underneath a lowercase character, that represents a vector, right? So it is essentially the mass of the particle times its velocity, vector v, right? So what Newton essentially has stated through the second law of motion is this, right? The net force acting on the net force F is going to be proportional to dp dt. Okay. Now this is the mathematical statement, right? So now the question becomes, how did it become F equals ma? Right? Any thoughts?
Differentiate that equation, linear momentum equation. Then m dv by dt is acceleration.
Okay, so let's do that. Very good. So dp by dt is going to be equal to d by dt of m, right? If I differentiate it, I use the product rule of differentiation. I get dm dt times v plus m times dv dt, isn't it? Do you agree? Okay. So this is a the acceleration dv dt, right? But then I have the first term, right? What do I do? So when we write ma, you and I are implicitly assuming that mass is constant. Okay, once we assume constant mass, okay, dm dt is 0, right? Then we get the time derivative of the linear momentum to be times a. That's fine. Okay, that is one step, right? So you can immediately see that, you know, like we can't use f equals ma everywhere, right? So we can only use it when we have a constant mass. Okay, so on the other hand, let's say, you know, like you have an application where, let's say, there is a launch of a space vehicle, right? So wherein when it launches from the base station on the Earth, correct? So it has a lot of mass, but then like as it goes higher and higher in altitude, it's going to jettison various objects, right? So obviously I won't use f equals ma, right, to model the entire motion of the space vehicle, right? So this is one important assumption, right? So behind f equals ma, but still we are only getting f to be proportional to ma. So this gives us f to be equal to some k times ma, where k is a constant of proportionality or proportionality constant, right? So is it not? Okay, k is a proportionality constant. Now, how did we get f equals ma now? Obviously, if k is equal to 1, right? So the answer is clear, right? My question to you is how or when, to be very precise, when would we have k to be equal to 1? And we can use f equals m. Okay, so these details are extremely important for us. All right, so please think about it. Does anyone have an answer to this question? Under what conditions this constant of proportionality becomes equal to 1? Okay, so please think about it. Okay, and then like we will continue from here in the next class. All right.
When G is equal to 1, sir, gravity is like a
G
gravitational
equal to 1. Okay.
2G, 3G, 4G. Like.
See, in vehicle dynamics, we essentially normalize acceleration by G. Okay. Yeah. So,
Okay.
but then, or we specify acceleration in terms of G units within quotes. All right. But the reason here is slightly different. Okay. So please
Okay.
do think about it. We will discuss in the next class. Okay. So kindly search till then, you know, like think whether you can find the answer and then we'll discuss. Okay.
Yeah.
Okay. Any other questions on what we discussed today? That's all. All right. Okay. So if not, I will stop the recording. Thank you.